Hello, this is James Combs, and I'm going to be doing the NACA 4424 airfoil in Ansys Fluent. The first step to do this is to go to Airfoil Tools, Airfoil Generator. Since it's a 4424 airfoil, the maximum camber is 4%, maximum camber position is 40%, and the thickness, the last two digits would be 24. And then for this airfoil, I'm gonna be using 200 points to make up the airfoil. I'm gonna plot this, set the plotter, make a chord length of 1000 millimeters because that corresponds to 1 meter, and everything else stays the same. I will plot this and get a CSV file of my coordinates. Now it'll open in an Excel file where I'm gonna just copy all this data over here. And from trial and error, I found that for these, um, for the points that have an X value of greater than 1,000, you need to lower them down to 1,000, so that it won't cause any issues. I don't know why, but even though that my chord length is 1,000, uh, in airfoil, in the airfoil tools, it'll create an airfoil that is more than 1,000 chord length by a very slight amount. This I'll also fix to be 1,000. After that, so that it'll translate well into Ansys Fluent, I will copy paste numbers 1 in this column right here. In this column here, I will copy and paste the numbers 1, 2, 3, 4, so on, just in increasing order. In this column here is the X value, the Y value, and the Z value. Because it is an airfoil and it's 2D, the Z value is always going to be 0 because that's how it is for a 2D object, like an airfoil. Now all of this data here, all these coordinates, will be sent into a notepad file, which will be saved as a .txt file. So let me should really quickly save this as Ansys Fluent video NECA 4424 coordinates. So there is our coordinates saved as a .txt file. Now let's open Ansys Workbench. Alright, so now the Ansys Fluent Workbench is open, I'm going to be starting a new Fluent project. And now that I have this, I'm going to go into Design Modeler Geometry, and I'm going to model the airfoil, inlet, outlet, and all that stuff. So it should load up in just a moment. All right, so the first thing to do, because our design, because of our airfoil's coordinates is in millimeters, we need to change our units to millimeters here. After that, we're gonna import our airfoil coordinates as a 3D curve. So I'm just gonna go ahead and go to where is it? Create a 3D curve from coordinates file. And with the coordinates file, I'm gonna be selecting what I just made. So it should be, yeah, this one here, the one from the video. And so it'll be in millimeters in the XY plane. So that should be good. I'm gonna click generate. And now if I align myself with the correct axis, it should appear, which, yep, it looks pretty good. Now I'm just gonna go ahead and uh, create a little line that connects these edges here. So let me go ahead and create or lines from points, point segments here to here, here, yeah. There we have a line that connects and that completes our airfoil. So now to actually make this into like an actual airfoil object, I'm gonna um, select surface from edges. So yeah, let me generate this. Then surface from edges. The edges I'm gonna select are this and the tiny, tiny little edge here at the end. And once I click generate, now we have an airfoil. The next thing to do now that we have our airfoil is to create our domain, which we're going to be creating a C-shaped domain to simulate different angles of attack. So the first thing to do is to create a new sketch. In this new sketch on the XY plane, I'm going to start off with a line that's on like the chord line that's about a quarter of the way through so that we're able to split this front part into its own section later on. I have to create a little like a box around this. I'm gonna start a quarter of the way to the front so that we can make its the front section its own part. I'm gonna create a line that is 5,000 in length here. Create another line that is 5,000 in length right below. Since both of them have to add up to be 10 meters or 10,000 millimeters, they both are 5,000. Then now I draw a line that's 10,000 millimeters or 10 meters to horizontal. And then I finish the rectangle. I complete the rectangle. So I'm gonna trim away this little bit at the end. Yeah, so now that we have the rectangle, I'm gonna create a 3-point arc here for our C section or C, our C domain. Select these two and then make it like this. And now we can trim away this part here, since we don't need this at the moment. And then now we have our domain. I'm going to go back to modeling, and from there we can create a surface from sketch. So I'm going to go into surface from sketches, select this sketch here, apply, and then generate. So now we have our C domain. And since this domain kind of covers everything, I'm going to subtract this by using a Boolean. So I'm going to go to create Boolean, and we're going to subtract this off. So I'm going to click subtract. Target bodies, we are um is it our target body is this overall thing, and our tool body is going to be the airfoil itself. So we'd have to double click that, select that, and then once we generate the Boolean, we'll have the airfoil as sort of it's not shaded in because the air does not go through the airfoil since it acts as like a wall, pretty much a wall in the shape of an airfoil. All right, so now that we have our Boolean done, now we can create the lines to make our projections, which allows us to separate our airfoil into various different zones, each meshed in a different way to produce a mesh that um, accurately captures the flow around the airfoil. So using this little point from before, we're going to create a sketch, create a vertical line that extends out from here. So vertical line, and then we're going to create a vertical line that goes from here to the front of this C um this C domain. Create some horizontal lines from it to complete our projection area. And then from the trailing edge, we're going to separate this into its own zone as well. So from the trailing edge, yeah, find it. Or I guess not necessarily from the trailing edge exactly, but just anywhere we're going to create vertical lines. And then we're going to dimension these vertical lines to be exactly 1,000 away from what do you call it? To be 1,000 away from the leading edge, because that's what defines the chord length. At 1,000. So now this will be, if you zoom in, it'll be exactly the on the trailing edge. From there, we're just going to create one more line that'll extend all the way to the end of this C domain. So let me start it right here. And then using the extend line tool, we're going to extend these lines all the way to the edges of the domain. All right. And then so now that we have these this sketch done, we're going to go back to modeling. We're going to go to create lines from sketches, and then using the sketch that I just made here, we apply that. We're going to generate these lines, and these lines will create the zones of meshing that we're going to be using in the next part. So to do that, we're going to go to projection, create projection, or tools projection. And for edges of the projection, we're going to be using these lines here. So holding control, I'm gonna select all of these. And then our target is gonna be this actual domain itself. And using that, generate that. It'll create these separate zones that we can highlight. And with these separate zones, we'll be able to mesh our airfoil. All right, so now that we're done with the geometry part, we're going to move on to meshing now. I'm going to double click the mesh and then it should load up the mesh that like the setup for the mesh that corresponds to what I made in the geometry part. It should just take a minute to load. All right, so now that it's loaded, I just need to turn these edges here into just like parameters for sizing the meshes along this C domain. So what I'm going to do is first of all in geometry, I'm going to suppress this because that'll just interfere with what I'm going to do. And in meshes, I'm going to select sizing and then select these seven walls for the first part of the mesh sizing. Select that and apply. And for height, we're going to select number of divisions equals 250. That's what I found works best. And to make the mesh more accurate, we're gonna introduce a bias. And what I found is that a bias factor of 50,000 works best for these walls here. And just like if you zoom in, if you do 100 bias of 100, you'll find that everything works out just about well, except for this one. So we're going to need to reverse the bias on this because the bias is incorrect. So reverse bias on this and set that back to 50,000. So now that that's done, let's move on to the next edge sizing. Edge sizing, and then now we're going to do these three. So select this, this, and this. Once again, doing number of divisions. It gave me an error for some reason, but number of divisions equal to 300. And we will have capture curvature, no, behavior, hard, and bias, same bias as last time, with the bias factor of 300. And as you can see here, where is it? And as you can see, for the bias, everything seems good, so we don't need to reverse the bias on any one of these three. Yep. Let me go back here, turn off capture curvature, and set this to soft. Now for the next sizing, I'm going to be doing these four surfaces along here. So I'm just going to select, I'm going to go ahead and select this if I can. This, this, and this right here. So that should be four edges. With those, I'll turn off capture curvature once again, set that to hard. I will make it number of divisions equal to 150. And in this case, since it's along the airfoil, there's no need for any bias on here, so we're good on that. Next sizing will be the front section, like the front, like the C part of the C domain. So I'm going to go ahead and just select these four edges right here. Apply, type, number of divisions, set that to 100. And once again, it's the front, so there's no bias necessary for this. Let's turn off this, set it to soft, no bias necessary. Now, because I had to do some additions to my airfoil, and there's a little flat part at the end, we're going to have two more edge sizings that normally you wouldn't need. So I'm gonna size up this edge right here. 1, 2. Apply. Once again, number of divisions. What I found here is that about 180 works well. Turn off this. Set it to hard. And for this, there's no bias necessary because it's right on the airfoil itself. And then just because there's a small little gap here, we're going to need one more edge sizing. So let me select this. It's very small. Very small, but select that. And what I found is that the number of divisions equal to about 8 approximates things pretty well. Makes these sizes about equal to this. So select that to 8. Turn off capture curvature, set it to hard. No bias necessary on this. So now that we're done with this, what we need to do is face meshing. So face meshing. The geometry we need to select are all 6 of these sections here. So 1, 2, 3, 4, 5, 6. And we're going to set to quadrilaterals because that's what we want to create for our mesh. So let's generate this mesh really quickly. Hopefully this works. Should load up in a second. Yeah, so now that we look at the mesh, it seems to have generated correctly. You have really small meshing regions around the airfoil itself to capture the movement around the airfoil, and then also small meshing quadrilaterals in the wake region, which will help us simulate the wake and the effects of that more accurately. You have the quadrilaterals kind of curved around here properly right in the C domain, and that in the mesh in the areas here that are less important are larger, which would help reduce computational time without changing results very much. So now we have that, all we have to do is create named selections. All right, so after creating the face meshing and doing all the edge sizing, what we have to do is create our edge selections and basically telling the program what our airfoil inlet and outlet are so that we can use that in our analysis. So to do that, what we have to do is select all the faces of the airfoil first, or any order, but I'm going to start with the airfoil. So this edge, this edge, this edge, this edge, and then can't forget about the tiny edges here. 1, 2, and then if you zoom in even further, this last edge here. So now that that's selected, you right click and select create name selection. We're going to call it airfoil because this is the boundary for our airfoil. So select that. That's our airfoil. And now for our inlet, the air will be coming in through here, but since there's no like walls here, we're going to also call this area our inlet as well. So I'm going to go ahead and select this, 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 this. Right click again, just like we did before, and create name selection and call it inlet. And then since the air is going to be coming out of here, we're going to call this outlet. So select those two, right click, create name selection, outlet, click apply. And now just to verify that everything is correct, select the airfoil, and the whole entire airfoil, including this whole back edge here, should be selected. If you clicked inlet, you'll see that this whole C shape of this C domain is selected, and for the outlet, you have this back wall selected. 1 second. Yeah, it should be all selected. I don't know why. I think this is just like a little thing on the program, but anyways, now that we're done, I'm gonna save project, and then go back to Workbench, exit out, go to Workbench, and then we gotta update the mesh so that it'll translate into the setup. So click update. All right, so now that we have a check mark, we're able to move on to our setup. All right, so now that meshing is complete, I'm gonna go on to the setup. Just double click on setup and it'll load up. No double precision is needed because I'll just increase the computation time. And I have 10 cores on my computer, so I'm gonna choose 8 for this number. And I'm gonna click start and it'll load up. All right, so now it's loading up. All right, now that it's done loading up, I'm gonna go to models first of all. Go to viscous models, change that the to this model right here, and I'm gonna change this to strain vorticity based. And then for fluids, we're just gonna make sure that it's air, because it's air going around the airfoil. So it is air, and I'm gonna change this density to 1.2 as the problem statement says, and I'm gonna change this to 1.8 times 10 to the negative 5. So I'm gonna just change that right real quick. Make sure the settings stayed. Yeah, that's all good. And the solid, it doesn't really matter what it is. It's just a wall anyways. All right, so now after that, if you go to boundary conditions, go to inlet. Since the Reynolds number is 1 million, the the velocity that corresponds to that would be 15 meters per second. So I'm just gonna select 15 right here, and then it'll be magnitude would be magnitude and would be components, or it would be magnitude and direction. Since if it were normal, it'd be coming from all sides, which it isn't. If the angle of attack is 0, it'll just be coming horizontally, and we can adjust angle of attack using this, which I'll do later. So if it is horizontal at 0 angle of attack, then it'll be all in the x direction. So select that and change the turbulent viscosity ratio to 1. So change that, and then and then just make sure that the outlet is just the outlet that we specified, and the wall is our airfoil. Just make sure that is true. And for reference values, you have to go there, verify that it is 1 meters per second. That is this 1 meter squared because our chord length is 1 meter, so our area should be 1 meter squared. Um, and then for all the values, we're going to compute this from the inlet. Verify that everything else is accurate. And then after we confirm that everything is accurate, then we go to report definition. In report definition, we want to say that we want to make it compute the coefficient of lift and the coefficient of drag. So I'm going to go to force report and lift for the coefficient of lift. I'm going to name it CL. It'll be lift coefficient here on the airfoil. And as far as the force vector, it'll just be all in the y direction and not in the x for a 0 angle of attack. Select all of that. Select a frequency of 10. And then go to drag coefficient on the airfoil, and it'll be all in the x for 0 angle of attack. Once again, print a console frequency of 10. I'm gonna rename this. I'm gonna rename this CD. Just rename this CD. And then after that, I'm gonna go to methods. And methods, I'm gonna be changing this to second order upwind, and everything else remains the same. And then finally, we go to initialization to initialize our simulation. Select hybrid initialization and click initialize. And then once it's done initializing, we can finally calculate. But actually, before that, we do need to change the residual, so our simulation will run smoothly. So in order to run the calculation, we're going to need to change the residual. And to do that, all right, in order to change the residual, you have to go to monitors, click residual, uncheck all this stuff here because we don't need it, and then change this here to 1 times e to the negative 7. So, and then iterations to plot 1000. And then finally, now that we're initialized, we can go to our calculation. So to run it, we just check everything here is all good. 1000 iterations with, what is it? A reporting interval of 10 and a profile update interval of 10,000 iterations. And once that's good, we just click calculate and wait for Ansys to give us the solution. All right, and now that it's done its 1000th iteration, the calculation is complete. So I'm gonna click OK right here. And then our data is on this 1000th iteration mark here. We find that the coefficient of lift is 3.25 times 10 to the negative 1. And then our coefficient of drag is 1.59 times 10 to the negative 2. So that's our values for CL and CD. Now, if you want to change the angle of attack to, let's just say 3 degrees, for example, we want to convert this into radians. So I'm going to say equals radians, put in 3. And then from there, since it's that many radians, let's compute the sine of that. So equals sine of this for one component, and then equals cosine for the other component. So now that we have these components, we're going to want to change some of the values. So copy this, go back into Fluent, and then we're going to want to change the inlet because if the angle of attack is different, the inlet velocity will be different. So we want to go to inlet, inlet. It's still 15 meters per second, but the x component would be this, and the y component would be this. And then for the lift, coefficient of lift, you want to change this to a negative of this number here. Change the y to this. And then for drag, you change that to this. And then the y component is just regular positive of this. And then once you reinitialize and then run the calculation, you'll get the CL and CD values for any angle of attack using this method.